This is the fourth in a series of screencasts looking at energy systems. This screencast will focus primarily on the aerobic energy system. So firstly, the term aerobic means that oxygen is being used. A couple of key points: glucose from our muscles or liver, and fats, fatty acids and triglycerides are the major food fuels. Fatty acids are the fats found transported in the blood. Triglycerides are the fats that are in the muscles that will be used for ATP resynthesis. During rest, fats are the primary fuel. So at rest, we're looking at approximately 2/3 fats and therefore about 1/3 carbohydrate. So that's at rest. During exercise, carbohydrates are the primary food fuel, and now that will depend on both intensity and duration. The greater the intensity, the greater the proportion of carbohydrates. Over a longer period of time, such as the next point, available carbohydrate stores may become depleted, so fats are then the only available viable food fuel. Now, because fats require more oxygen to produce or to resynthesize the same amount of ATP, the cardiorespiratory system will have to work harder to deliver more oxygen. So, question: what will happen to the rate of ATP resynthesis if we run out of available carbohydrate? If that does occur, then we have to decrease our rate of energy resynthesis because it takes longer to break fat down than what it did carbohydrate. If it's taking longer to break it down or to resynthesize ATP, that means that the rate of production decreases, therefore our output intensity will also decrease. The anaerobic system is used to produce energy for activities of a low working intensity. So here we're looking at 70 to 85% max heart rate. System allows for peak aerobic power production from approximately 60 seconds and will be the major provider of energy for muscular contraction after 30 seconds. So, aerobic system, 70 to 85% max heart rate. Anaerobic glycolysis, 85 to 92% max heart rate. ATP PC, 92+% max heart rate. So that is the percent max heart rate that we would, or range that we would expect to be given information on to be able to solve questions. So a couple of examples. Percent time spent in percent max heart rate zones is 0 to 70, 70 to 85, 85 to 92, 92 plus, and here we're looking at percent max heart rate. So this is suggesting that 15% of the time was spent between 0 to 70. 20% of the time between 70 and 85. 40% between 85 and 92. And 25 at 92+% max heart rate. So here we were asked the first question, what percentage of ATP resynthesis, or what total percentage did each energy system provide for that activity? Here we could say that the ATP PC system provided the 25% of energy for the activity, the anaerobic glycolysis 40%, and the aerobic 35%. Because obviously, even though we're looking at 0 to 70% here as a zone percent max heart rate, the aerobic system will still be the predominant energy provider at recovery or rest. So how does the aerobic system actually produce energy? So we start off with glycogen. And the glycogen is converted to glucose. We have glycotic enzymes that work to break down the glucose. As a result of the glycotic enzymes breaking down the glucose, we have energy being released. Now that energy is used to resynthesize to ATP. Byproduct here of the breakdown of glucose is pyruvic acid. Now the pyruvic acid enters what's known as the Krebs citric acid cycle. So the pyruvic acid enters the Krebs citric acid cycle. Fats also enter the Krebs citric acid cycle. And here we have oxidative enzymes. Now these oxidative enzymes help break down the pyruvic acid and the fats, and as a result of that, energy is released, and we have enough energy to resynthesize to ATP. Now, from this, hydrogen ions are released as a byproduct of. These hydrogen ions enter what's called the electron transport chain. So the hydrogen ions enter into here, and again with our oxidative enzymes, the breakdown and the conversion of the oxidation, of hydrogen ions, enough energy is released to resynthesize 32 to 34 ATP. We have a couple of byproducts in here as well. We have water, carbon dioxide, and heat. So in total, we are able to resynthesize 2, another 2, 32 to 34 ATP. So in total, we can resynthesize 36 to 38 ATP via the aerobic energy system. A couple of slides from ERA that look at this as well. So here we're looking at glucose being broken down, resulting in pyruvic acid, glycerol being broken down as well, 2 ATP here, the glycerol entering the Krebs citric acid cycle, and our pyruvic acid entering the Krebs citric acid cycle, releasing enough energy to resynthesize another 2 ATP. Now, hydrogen ions ending up there, entering our electron transport chain, where we can resynthesize 32 to 34 ATP with water, heat that have been given off. Another way of looking at it, which was fairly similar to what I drew, glycogen to glucose. Obviously here we have our glycotic enzymes working on this, releasing energy for energy resynthesis, pyruvic acid, fats, and our pyruvic acid entering the Krebs citric acid cycle, again releasing energy for ATP resynthesis, hydrogen ions, then entering our electron transport chain, again resynthesizing ATP for muscular contraction. So a worded example. My feeling is that if you can draw the flow chart, then you would be able to write a description for that flow chart. I would find that personally easier to do than learning just the sentences. So again, just a breakdown, 2 from glycolysis, so the breakdown of glucose, 2 from within this Krebs citric acid cycle, and 32, 34 from the electron transport chain, leaving us a total of 36 to 38. Byproducts, carbon dioxide, water, and heat. Now, our relative contributions of carbohydrates and fats will depend on intensity, and as intensity increases, so does the contribution of carbohydrates. The greater the intensity of work, the greater the proportion of fuel that is carbohydrate. So looking at VO2 max, or our maximum oxygen uptake, this is the maximum amount of oxygen we can use per minute to produce and resynthesize energy. So a maximum amount of oxygen that in 1 minute that can be delivered to, uptaken by, and used by the muscles to resynthesize ATP. Now notice that we have a per kilogram in our measurement here. This enables us to compare VO2 max levels between athletes of various body shape sizes. So less than 50 milliliters per kilogram per minute, we would suggest was a club athlete, a trained athlete somewhere between 50 and 60, and a highly trained athlete would have a VO2 max of above 60. So now looking at energy production during exercise, and this is looking more at the interplay between the energy systems. So here where exercise is beginning, intensity is increasing from rest. We can see that as our oxygen consumption will increase. Now, a line across here represents energy demand. So at the beginning, because our heart rate takes a little while to increase, our respiration rate takes a while to increase, tidal volume, etc. It means that the anaerobic energy systems are going to have to provide the majority of the energy, with the aerobic system providing a little. The further we go into the event, we'll see that the aerobic system will start providing more and our anaerobic systems providing less. The anaerobic energy production is referred to as oxygen deficit, and previously the oxygen that was required above resting levels, so what we now call EPOC, excess post-exercise oxygen consumption, this was referred to as oxygen debt. Again, EPOC, oxygen debt have two parts to them. The first, which is the quick part, is the replenishment or resynthesizing of our ATP and CP stores. And the second part, which is the slow part, is the oxidization of lactate and hydrogen ions. So essentially, oxygen deficit is the amount of energy that has to be produced by the anaerobic energy systems to meet our energy demand. Again, just a worded description there of our oxygen debt. The second part, or the slow part, lactic acid debt it used to be called, the oxygen required to break down and remove lactic acid, so that being our lactate and hydrogen ions. The first part, or the fast part, the oxygen required to replenish muscle stores of ATP and CP. So this is the interplay of energy systems working above 110 or working at 110% VO2 max, so above 100% VO2 max. So the first question then is, how can we work above 100% VO2 max? Well, 100% VO2 max is simply what your VO2 max is. So the maximum amount of energy that can be resynthesized aerobically in a minute. But we also have two other energy systems. We have the ATP PC energy system, and we have the anaerobic glycolysis energy system. Now, presuming that these two energy systems make a contribution, then we can work at a level that is above 100% VO2 max, because here the anaerobic energy systems make a contribution. So looking at this graph here, are there points in time where the anaerobic energy systems allow for a level of intensity greater than which the aerobic system could provide on its own, so above 100% VO2 max? So here, where the ATP-PC system is making a contribution, well, it's making a contribution and it's above the line of the aerobic system. And even if it's under the line, it's still making a contribution. So in this area here, we're certainly working well above. Looking at the anaerobic glycolysis system, well, it's making a contribution all the way through to there. So all of this energy production is sitting on top of what the aerobic system is as well. So this is the aerobic contribution. So as we can see here, we have an energy demand line. What was being produced by the ATP-PC system, in essence, we could sit on top of this for a second. So here's our aerobic energy production. If we add on top of that what's being contributed by the ATP PC system, and then we add on top of that what's being contributed by the anaerobic glycolysis system, we can see where our oxygen deficit is occurring. And the oxygen deficit in this would be this area here, the bit that sits above what the aerobic system is contributing. And again, this is from the beaker. This is looking at for a particular activity. So here, a 15-second event, not the 15-second mark of a 240-second event, but this is a 15-second event. So what this is saying is that for a 15-second event, 88% of the energy will come from anaerobic, so it could either be ATP, PC, or anaerobic glycolysis energy systems, 12% aerobic, and so on. And it's in here where we go from a predominant anaerobic contribution to a predominant aerobic contribution. So it would be fair to say that at approximately 0 through to 75 seconds would be around about a 50-50. So this is looking at different distances. So first one, a 400 meters that's run in 52 seconds, 54% anaerobic, 46%, make it a bit clearer, 46% aerobic, 31% anaerobic. This is now for an 800 meter runner, 69% aerobic, 1500 meters, 17% anaerobic, 83% aerobic. Now, one of the things to notice on this is a visual of a concept where our anaerobic energy systems are finite. So they have a finite capacity. So although we go from 52 seconds up to 118 seconds, up to 242 seconds, the actual amount of energy, not percent, but the amount of energy produced by the anaerobic energy systems is very, very similar. The difference between them is the amount that the aerobic system will then contribute. So here, a 400 meter sprint, looking at oxygen uptake, oxygen deficit throughout the 400 meter run. We can see that all the way through the event, we are working well above our VO2 peak. So this could look at to be our energy demand. So here, oxygen deficit. So this bit here, oxygen deficit, that represents the amount of energy that is being produced by the anaerobic energy systems. And we're well above our VO2 max here. Going to an 800 meter sprint, we'll see that we're working not quite as much above our VO2 max. So again, if that was our energy demand, because we're working over a longer period of time, we're not able to maintain intensity. So our VO2, the amount that we work above VO2 max decreases. Again, oxygen deficit here representing anaerobic energy system contributions. 1500 meter sprint. Again, energy demand here is even less above our VO2 max. And yet again, oxygen deficit representing the contribution from the anaerobic energy systems.